which is being passed from the compressor.
Perdón, ¿sí se oye y sí se ve?
Sí, profe.
Sí, profe.
Ok, sigue.
And fuel from the fuel spray nozzles in order to generate the maximum heat release at a substantially constant pressure, so that the turbine receives a uniformly expanded, heated, and accelerated stream of gas. This is not an easy task, but advancements are constantly being made in combustion chamber design to enable more efficient use of fuel with less and less pollution of the atmosphere. Efficient combustion has been made increasingly more important because of the rise in the cost of the fuel, and also the increasing awareness of the aviation industry and the general public of the dangers of atmospheric pollution from the exhaust smoke. There is a limit to the maximum temperature of the gas exiting from the combustion chamber. This is imposed by the materials from which the nozzle guide vanes and the turbine blades are manufactured. The slightest excursion above that temperature limit will mean distortion of the turbine blades and the possible disintegration of the turbine, with probably catastrophic results. Modern turbine and nozzle guide vane materials will allow a gas temperature not exceeding 1,700 degrees Celsius when it exits the combustion chamber. Considering that the air which leaves the high-pressure compressor may already have been heated to around 550 degrees Celsius during its compression, we can add sufficient fuel to raise the temperature of the gas exiting the combustion chamber by a further 1,150 degrees Celsius before we exceed the limit temperature of 1,700 degrees Celsius. It must also be remembered that the combustion chamber has to be capable of maintaining stable and efficient combustion over a wide range of engine operating conditions. Of course, 1,700 degrees Celsius would be the temperature of the gas exiting the chamber with full power selected. Lower power settings would require lower fuel flows and consequently would generate lower gas temperatures. You'll see from this graph that the air enters the combustion chamber at a slightly slower rate than which it enters the intake of the engine. Speeds of around 500 feet per second are not unusual. The flame rate of kerosene, that is, the speed at which the leading edge of a flame would travel through kerosene vapor, is approximately 30 feet per second. If burning kerosene was exposed to an airstream which was traveling at 500 feet per second, it would be extinguished immediately. So, something must be done to slow down the speed of the airflow after it leaves the compressor and before it reaches the combustion chamber. Otherwise, the flame would not be sustainable. At this position on the graph, we see how this reduction in the velocity of the air is achieved. The air is slowed down, and, an added bonus, its pressure is increased after it leaves the compressor by passing it through a divergent duct immediately before it enters the combustion chamber. In fact, the pressure attained at this point, at the end of this divergent duct, just before the air goes into the combustion chamber, is the highest in the whole of the engine. The reduction in velocity is still not enough, however. Further decreases must be achieved if the flame is not to blow out. The air is divided after it exits the high-pressure compressor into primary, secondary, and tertiary airflows. We'll now examine each of them. This diagram shows how the air entering the flame tube passes through the snout before being divided to go through the perforated flare and the swirl vanes and into the primary zone. The primary zone is a region of lower velocity recirculation, positioned immediately downstream of the fuel spray nozzle. It's within this zone that stable combustion is achieved. The primary air is approximately 20% of the total airflow coming from the high-pressure compressor and into the combustion chamber. This is the air which is mixed, in a ratio of approximately 15:1 by weight, with the fuel and burnt. By being passed through the flare and the swirl vanes, the velocity of the primary air is reduced, which must happen if the flame is not to be extinguished, and the shape and position of the flare and swirl vanes also starts the air recirculating within the region. The remaining 80% of the output of the high-pressure compressor, air which has not been directed through the snout, goes into the space between the flame tube and the air casing. Some of this remaining air, approximately another 20% of the output of the high-pressure compressor, is allowed into the flame tube through secondary air holes. This air is called secondary air, and it reacts with the primary air, which is flowing through the swirl vanes to form a toroidal vortex. The toroidal vortex stabilizes and anchors the flame and prevents it being moved through the flame tube away from the fuel nozzle area. The temperature of the gases at the center of the primary zone reaches about 2000 degrees Celsius. This is far too hot for the materials of the nozzle guide vanes and turbine blades, so a further drop in temperature is required before the gases can be allowed to exit the combustion chamber. The remaining 60% of the total air coming out of the high-pressure compressor is progressively introduced into the flame tube through corrugated joints and dilution air holes in the flame tube. This air is called tertiary air. Tertiary air is used to cool both the air casing and the gas exiting the chamber. The type of combustion chamber which we have used to illustrate the interaction of the flame and the cooling air is representative of those which would have been used in an early multiple combustion chamber system. Different methods of keeping the combustion chambers from overheating are used. Some flame tubes have ceramic-coated tiles fixed to a skin on their interior walls. Cooling air passes through the holes in the skin and flows between the skin and the tile, which has a ridged surface. The ridged surface improves the heat transfer between the tile and the air. The air finally enters the flame tube at the front and rear of the tile and forms an insulating film for the tile as it flows over it. Other engine designs use a different method of cooling the air casing, which is called transpiration cooling, where a film of air flows between laminations, which form the flame tube wall, and then exits the laminations to form an insulating film of air within the flame tube. This picture illustrates several other features of the type of combustion chamber which would be used in a multiple combustion chamber system. Although the engine would probably start quite readily with only one igniter operating, most gas turbine engines have two igniters. However, because there are only two igniters, another means of passing the starting flame between the combustion chambers in this type of system has to be found. This is called the interconnector. Immediately after light-up, the flame in the combustion chambers which have the igniters causes an increase in the pressure within those chambers. The pressure differential between a chamber which has a flame in it and those adjoining it which have no flames drives the burning gases through the interconnector pipework. When the burning gases come into contact with any unlit mixture in the adjacent combustion chamber, they ignite that mixture. This process is continued around the engine until the contents of all of the chambers is burning, whereupon the pressures within them are equalized and the flow through the interconnectors ceases. The sealing ring at the turbine end of the combustion chamber allows for elongation of the chamber due to expansion. The chamber is fixed at the compressor end by being bolted onto it, and it cannot expand in that direction. The sealing ring allows the chamber to expand into the nozzle box, which is the portion of the engine immediately preceding the nozzle guide vanes, while maintaining a gas-tight seal between the chamber and the atmosphere. The straight-through flow multiple combustion chamber system was developed from Sir Frank Whittle's original design, which was supplied with air by a centrifugal compressor. The straight-through combustion chamber system was later used on some earlier types of axial flow engines, and is still in use on centrifugal compressor engines such as the Rolls-Royce Dart. The multiple combustion chamber system consisted of a number of the individual combustion chambers, which are shown here. Each combustion chamber consists of a flame tube, which has its own air casing. The combustion chambers are disposed around the engine just to the rear of the compressor section. This picture shows a multiple combustion chamber system similar to that used in the Rolls-Royce Avon, which was a powerful, for its time, axial flow compressor engine used on many different types of aircraft, both military and commercial, fighter and transport, for a considerable number of years. Shown here are the snout, the primary air scoop, the interconnectors, and the drain tubes. The drain tubes allow the drainage of excess fuel from the combustion chambers in the unlikely event of the engine failing to start, an event which is more commonly called a wet start. A wet start happens when the mixture of air and fuel in the combustion chamber fails to ignite during a start. A considerable amount of fuel will have been fed into the combustion chamber during the attempt to start. If that fuel is not removed before the next attempt to start, and if that attempt is successful, the result will be a combination of excessively high gas temperatures in the turbine region and torching, which is the name for a very long, very hot, and very dangerous jet of flame issuing from the rear of the engine.
Vamos al número 2, a la parte 2.
Two means of getting rid of the fuel are open to us. First, the fuel drain system. And second, a method of evaporating the remaining traces of fuel from the combustion chambers, the turbine, and the jet pipe. The fuel drain system utilizes the drain tubes which connect the lowest part of each chamber with the next chamber below it. Fuel remaining after a wet start will attempt to find its own level by flowing from the top of the engine to the bottom chamber. Once in the bottom chamber, the excess fuel exits the engine. Any remaining traces of fuel within the engine must be evaporated. To this end, the engine must be motored over on what is termed a blowout cycle. During a blowout cycle, the engine is turned over by using the starter motor. It's rotated for the time normally allocated to a full start cycle, but with the high-pressure fuel cock shut and the ignition system deselected. Air from the compressor will flow through the combustion chambers, the turbine, and the exhaust system, and assist in the evaporation of any fuel still remaining within. The tubo-annular combustion chamber system, shown here, is sometimes also called the cannular or can-annular system. The tubo-annular combustion chamber system differs from the multiple combustion chamber system insofar as it does not have individual air casings for each of the flame tubes. A number of flame tubes are fitted within an inner and an outer air casing, which makes this system a more compact unit.
Es el tipo can-annular.
Notice the position of the igniter plug. This illustration is of a typical example of an annular combustion chamber system. It has only one flame tube, which is contained by an inner and outer air casing. The annular system has several advantages over the multiple combustion chamber system and the tubo-annular system from which it was developed. They are...
Son los tres tipos de cámaras de combustión, las de cámaras de combustión de tipo individual o de bote, o can, ¿verdad? Que significa bote, las de la combinada, las cajas, sí, las cubiertas o cajas exterior e interior es anular, pero los tubos de fuego son individuales. Aquí en la de bote, cada cámara de combustión tiene adentro su tubo de fuego, el flame tube que estuvieron oyendo. Y el último tipo de cámara de combustión es el anular, donde tanto la caja exterior y la caja interior son anulares, y el tubo de fuego también es anular. ¿Ok? Son los tres tipos.
For the same power output, the length of the annular chamber is only 75% that of a tubo-annular system of the same diameter. There are no flame propagation problems. Compared to a tubo-annular system, the air casing area is less. Consequently, less cooling air is required. The combustion efficiency is raised to the point where unburnt fuel is virtually eliminated, allowing the oxidization of carbon monoxide to non-toxic carbon dioxide. There is a much better pressure distribution of the gases impinging on the turbine, so it has a more even load placed upon it. We stated at the beginning of this lesson that we had to obtain the maximum heat release from burning the mixture of fuel and air in the combustion chambers. To do this, we must use the chemically correct air-fuel ratio of 15:1. Whereas in the piston engine the use of the chemically correct air-fuel ratio of 15:1 would cause detonation and dissociation to occur, in the gas turbine engine it poses no such problem, because there are no peaks of pressure to assist in their generation. The fuel and air are therefore mixed and burnt in the primary zone of the combustion chamber in the ratio of approximately 15 units of air to 1 unit of fuel by weight. The addition of secondary and tertiary air will, however, dilute the mixture to the extent that the overall ratio may vary from between 45:1 to as weak as 130:1.
Hay que hacer hincapié, el flujo primario es el que entra en la combustión, ¿ok? Pasa por el torbellinador y entra al interior del tubo de fuego. Y el flujo secundario es el que pasa entre el tubo de fuego y la caja exterior, o el air casing que le llaman aquí, pero se va introduciendo poco a poco en el flujo para la combustión y para el enfriamiento, tanto por afuera como por una capa laminar que queda aquí adentro, ¿ok? Flujo primario, flujo secundario para enfriamiento.
Profe,
Pueden ser preguntas de examen, ¿eh? Está en sus libros, ¿eh? De todas maneras.
profe,
Sí.
los porcentajes que manejaban ahí del 80 y 20% ¿se
Ujú.
calculan o ya son así?
Son genéricos. Es lo que se considera que pasa, ¿ok? En cada sección de la cámara. Continuamos.
In the introduction lesson, we stated that combustion theoretically occurs at a constant pressure. In fact, as is shown here, a small loss in pressure does in reality occur as the gas passes from the compressor end of the combustion chamber to the turbine end.
Está la caída de presión, ¿no?
This loss of pressure is caused by having to provide adequate turbulence and mixing. Losses vary from 3 to 8% of the pressure at the entrance to the combustion chamber. During normal engine running conditions, combustion is self-supporting. The ignition system is actually switched off as soon as the engine has attained self-sustaining speed.
Ya ven, se puede apagar el sistema de
Self-sustaining speed is the
ignición.
speed at which, after start, the engine can accelerate without the assistance of the starter motor. There may, however, be certain engine operating conditions which do require the use of the ignition system. For instance, just such a condition would occur following a flameout, which is extinction of the flame due to various unusual occurrences, such as the ingestion of large quantities of water thrown up from the nose wheels into the engine intakes during takeoff from a heavily contaminated runway. Combustion stability means smooth burning of the mixture, coupled with the ability to remain alight over a large range of air-fuel ratios and air-mass flows. This graph shows the limits of those air-fuel ratios and air-mass flows within which combustion will remain stable.
Límite de mezcla rica,
The graph shows that combustion stability will occur only between a narrower and narrower range of air-fuel ratios as the air mass flow through the engine increases. And beyond a certain level of air mass flow, the flame is extinguished. Outside the ignition loop, which lies within the stable region, it is more difficult to start combustion than it is to sustain it once it has started. Restarting the engine in the air while it's windmilling is called a relight. A consequence of this is that, should the engine flame out at high speed or high altitude, it may be necessary to slow down and or descend before the engine can be successfully relit. This graph illustrates a relight envelope for an imaginary engine, showing the flight conditions under which it would be guaranteed to relight if it was fully serviceable. The airflow through the engine will cause it to rotate or windmill, so the compressor is supplying sufficient air to support combustion. All that is then required is the opening of the high-pressure fuel cock to deliver a fuel supply and operation of the ignition system to add the final ingredient, a spark. Operation of the ignition system to supply the spark is achieved by selection of the relight switch. The electrical power to the relight ignition circuit functions independently from that which feeds the normal start circuit. Combustion efficiency is the efficiency with which the combustor assembly extracts the potential heat actually contained in the fuel. This graph shows the combustion efficiency of a modern gas turbine engine across the range of air-fuel ratios which occur during normal operating conditions. Modern gas turbine engines have a very efficient combustion cycle. At high power operating conditions, combustion efficiencies as great as 99% are achievable. And at idle, the systems will still give as much as 95%. The very high combustion efficiency attained in modern gas turbine engines is due in no small part to the fuel spray nozzles which are used in them. These nozzles have the task of atomizing or vaporizing the fuel to ensure that it is completely burnt. This is no easy undertaking, considering the velocity of the airstream from the compressor and the small distance available within the chamber for combustion to occur. Other difficulties occur as a result of the relatively low pressures attainable by the engine-driven high-pressure fuel pump at engine start. The pumps can be of the plunger type or the gear type. The pumps are fitted to the high-speed gearbox, which is driven by the high-pressure compressor shaft. The pumps are only rotating at a minimal speed during initial engine start, and are incapable at that speed of providing the high pressures, 1,500 to 2,000 pounds per square inch, required to give a good spray pattern. At engine start, when there is low engine RPM and low fuel pressure, the fuel spray pattern forms what is known as a bubble. This spray pattern is unable to atomize the fuel jet sufficiently for ignition to occur. As the engine accelerates during the start sequence, the pump rotates faster and builds up more pressure until the spray pattern forms a tulip shape. Atomization is still not sufficient to support combustion. Eventually, the pump produces sufficient pressure to shorten the tulip until it touches the orifice. Only now is the fuel jet atomized sufficiently to ensure rapid burning.
Recordarán los atomizadores duales, ¿no?
We've demonstrated then that a small orifice of fixed size will provide a finely atomized spray at high fuel pressures. However, when higher volume fuel flows are needed through larger bore nozzles, the pressures required from the pumps to provide that finely atomized spray become unattainable. Thus, for that type of situation, other methods must be found to sufficiently atomize the fuel at engine start when fuel pressures are low. The air spray system uses a high-velocity airstream to break up the flow of fuel. It requires only relatively low fuel pressures and can therefore operate using the gear-type pump, which is much lighter than the more sophisticated plunger-type pump. The duplex system, and shown here the duple spray nozzle, effectively use an orifice of variable size. At low fuel pressures, a pressurizing valve closes off the main fuel feed to the nozzle, the only supply coming from the primary fuel line. The primary fuel line feeds the primary orifice, a relatively small hole, which is capable of providing a finely atomized spray at lower fuel pressures. When the engine accelerates during start, fuel pressure builds until the pressurizing valve starts to open. This allows fuel to flow through the main orifice, where it will supplement the spray of fuel from the primary orifice. In the vaporizing tube method, illustrated here, the fuel is sprayed from feed tubes into vaporizing tubes, which are positioned inside the flame tube. Primary air is fed into the flame tube through the fuel feed tube opening, and also through holes in the flame tube entry section. The fuel is turned through 180 degrees, and as the vaporizing tubes are heated by combustion, the fuel is vaporized before passing into the flame tube. This concludes the lesson on combustion chambers.
Bueno, ya vieron tipos de cámaras. Si preguntamos cuáles son los componentes, ¿qué dirían?
The combustion chamber
Ahora vamos a ver este otro. Vamos a ver este. Que de pronto se parece al que vimos antes, no sé por qué. Vamos a ver.
The combustion chamber, or combustor, must contain the burning mixture of air, which is being passed from the compressor.
Lo quitamos. Mejor vemos este otro.
Hi, this is the fourth video on the topic of combustion chamber. I believe that if you have not gone through the previous video, try to view the previous video first before you go into this particular video. In this particular video, we will focus on the types of combustion chamber. And in terms of the different types of combustion chamber, there are three main types available for use in the gas turbine engines. These include multiple chamber,
que son los de
annular
anulares.
chamber, and annular chamber. I will explain to you the three types of combustion chamber. This is a typical early Whittle combustion chamber. Imagine there are many combustion chamber installed in one particular gas turbine engine. So the explanation of how combustion process works are already being explained in the previous videos. So this type of combustion chamber is used on centrifugal compressor. Normally it is for centrifugal compressor and earlier types of axial compressor, but very difficult to see it is in operation anymore. So the chambers are disposed around the engine, which I will show you in figure 4.7 later on, and compressor delivery air is directed by ducts to pass into the individual chambers.
¿Individuales o tubulares?
In the multiple combustion chamber,
O múltiples.
normally the individual can of combustion chamber are being placed in the circumferential of the engine, and it is interconnected to each other. So each chamber has an inner flame tube around which there is an air casing. So the air will pass through the flame tube snout and also between the tube and the outer casing. The separate flame tubes are all interconnected. So this allows each tube to operate at the same pressure. So you want the same pressure, and allows combustion to propagate around the flame tubes during engine starting. The second type of combustion chamber is turbo-annular combustion chamber. So this type of combustion chamber bridges the evolution gap between the multiple as well as the annular types. A number of flame tubes are fitted inside a common air casing. The airflow is similar to that already described in the multiple type combustion chamber, and I will show you in figure 8 how does it look like. So this arrangement combines the ease to overhaul and testing of the multiple system with the compactness of the annular system. So this is the picture of a typical turbo-annular combustion chamber. It is a combination of the can type, okay, and annular. So there is can as well as annular, okay, in the circumferential of the engine itself. Now, the third type of combustion chamber is annular type. So this type of combustion chamber consists of a single flame tube. There's no longer separated individual combustion chamber can, and it is arranged in completely annular form, which is contained in an inner and outer casing, as shown in figure 4.9. The airflow through the flame tube is similar to that already described in the previous two combustion chamber, and the chamber being open at the front to the compressor and at the rear to the turbine nozzles. This is a picture of a typical annular combustion chamber where you can see there is no longer individual can. So what we have here is just an annular type combustion chamber. So the main advantages of the annular chamber is that for the same power output, the length of the chamber is 75% of that a turbo-annular system of the same diameter, resulting in considerable saving of weight and production costs. Another advantage is elimination of combustion propagation. So it is a problem where combustion propagates from one chamber to another chamber. In comparison with turbo-annular combustion system, the wall area of a comparable annular chamber is much less. Consequently, the amount of cooling air required to prevent the burning of the flame tube wall is also less by approximately 50%. And this reduction in cooling air raises the combustion efficiency. So the efficiency increases to virtually eliminate unburned fuel that resulted to less pollution.
Casi la combustión es perfecta.
The introduction of the air spray type fuel nozzle to this type of combustion chamber also greatly improves the preparation of fuel for combustion by aerating the overrich pockets of fuel vapor close to the spray nozzle. So this will also result in large reduction in initial carbon formation and eventually increases the efficiency of the engine. And that's all for now with regard to types of combustion chamber. We will now continue to the next topic, which is combustion chamber performance.
Y ya vean de dónde es esto, de la University de Putra, Malasia. Ah, caray. Si quieren ir a estudiar a Malasia, pues ahí van a recibir estas esas clases. Déjenme ver. Esa es la lección que seguía del proceso de combustión. Vamos a ver este que es rápido. Ven tan rápido como ver las formas físicas, ¿no?
Hey everybody, welcome to Jet City. What are you doing? State your name and what you're doing.
Black wiring.
An Arenda OTF3, which is the same engine as the Canadair Sabre engine. It just doesn't fly. What does it do? What does it do, Missy?
I think it's the oil pump.
An oil pump?
Yeah.
That's going to pump a lot of oil. 10,000 horsepower?
Yeah.
Excellent. Okay, let's get to work. This video is a follow-up or a part 2 to good news, bad news, or bad news, good news with the T58. We have been salvaging parts from donor engines, and we've got the combustor out of the engine that burnt up, and the candidate for replacement right here. And we're going to take a look at the differences between the two. First, let's take a look at some of the damage to this combustor. Now, it wasn't really burnt by the heat, so I guess the air jacket survived for a while and was maintained so that this thing wasn't burnt up, but it was on the way out. Let's just show you a couple things here. Can you see that? There we go. There's pieces missing around the sealing edge. That would seal around a flange in the outer gas path, because all the hot gas is going to the turbine pass through here. This is the exit of the combustor. And there's also some damage right there. Can you see that? That was from vibration. And these pieces have already gone through the engine and have damaged it, but then the turbine burnt up, so no big deal. Also, it's got some age on it. There's some globby weld repairs there. And we're going to turn this over and compare it to the new one, which is right over here. Okay, before we take this thing apart, I'm going to show you one more case of wear, which shows that this combustor was really needing to be replaced anyway, even if the engine didn't self-destruct. So there are mounting bosses, or pin bosses. There's one right there. Right there. That's where a pin comes in from outside the combustor case, through the case, and holds the liner in place, because these liners essentially float in position to allow for thermal expansion, but it's located by a pin, and you can see that hole is quite worn. There's 4 of them. There's another one. Doesn't look so good. Very worn from vibration. There's the 3rd one. And the 4th one. Now, when these pins wear through, there's nothing really holding this combustor in place. And these are the fuel lines. They pass through a hole in the outer case. So they would then contact the outer case and wear and fret and eventually fail, which would be bad to be spraying fuel in an uncontrolled fashion all over the combustor and in it, and would be bad. Okay, we're going to take the cover off. Okay, before that, this is the old one. This is the new one. There's a couple differences we can look at, besides the fact that there's no wear. It's in really good shape. You know, look at the design here. This cover, it's over the fuel manifolds, which we'll look at in a second. It's a 2-piece with a screw on each side. and it's held in with 2 bolts around its circumference. All right. The new one has 1, 2, 3, 4 mounting bolts. It's all one piece, which I like. Less pieces to come apart. Also, the inner liner, or inner wall of the liner, has these locating slots that go over the struts that come out of the compressor. They're actually in the diffuser case, or the compressor outlet, whatever you want to call it. But they're just holes in the sheet metal, saddle-shaped grooves cut in the sheet metal. And on this one, they've got an extra sheet of reinforcing metal there, so it's a double thickness. I like that. It's starting to look like this one is not just in better condition, but it's of a newer, more heavier duty design. So let's pop the hood on each of these and compare them. Okay, so a little clamp here. Little clampy clamps that hold that on. There's 2 of them in this design. Okay. And then we've got to pull this apart. There we go. Come on. How do I do that? There we go. And they just sort of pop apart. And there's the front half, what I'm calling the front half. It's actually the bottom of the engine. This is on the top. Okay. And I've taken this apart before, so there's no lock wire. But let's do the other one as well. Okay, this one has 4 bolts with no little clamps. They just go straight into a threaded insert. Okay. And this one actually comes off just like that. I like that. It's one piece, nothing to rattle apart. Now let's take a look at both of these from the top. Okay, in the combustor that we're going to be replacing, it has a clamp here and a bolt, and there isn't a clamp over there. What holds the fuel manifolds down is this sort of this inner sheet metal bulkhead inside the cover. That's all right, I suppose. But on the one we're going to be using to replace it, there's a clamp, and they're quite heavy-duty clamps. The same as over here. They're the same part number. There's one on the entrance, or the inlet of the fuel manifolds. But unlike the other one, this one also has one holding down the other end. So I like that. And inside the cover, well, it's just a cover. I kind of like this design better. Makes me feel better. Okay, let's take off the clamp that holds the fuel manifold in. We'll take a look at the fuel nozzle. Now this has already been disassembled and just put back together to keep the pieces from getting lost. And so the fuel nozzles have already been cleaned. I did that yesterday. We're actually reshooting this video because it was all blurry after I took a look at the footage. So these are 8 of the 16 fuel nozzles in a T58, and they're exactly the same as the ones in the newer one. Each of these lines supplies fuel to 4 nozzles. Did I point out the same ones? I did. So there's an alternation. So I think 8 fuel nozzles in total are used for starting, and then once it gets going, all 16 are used. Let's take this manifold out, and there's one more design difference that I really like in the replacement manifold, the replacement combustor. And we'll take a look at that. Let's take a look at that. Okay, we've got the old one and the new one. I'm going to lift out the fuel rail. And again, these have already been cleaned. They were black and sooty when I took them out yesterday. Okay. Set them down very carefully. Let's see if we can get a nice close-up of what these things look like. Okay, those are the fuel nozzles, and they're the exact same. And they inject fuel into this combustor. The air in this combustor is at about 100 psi, so about 8 times more dense than atmospheric air. So a lot of fuel. Each of these combustors burns enough fuel to make about 1,300 horsepower at the power turbine. And let's take a look at a little difference between the two. In the old one, these are where the fuel nozzles fit. Let's see if I can light it up and move it around for you. They're pressed out of sheet metal. And what they do is they seal the fuel nozzle but still allow for some movement without letting air through. Okay, that's what they look like. And on the new one, they are much heavier duty, much thicker section. I'm trying to get the lighting good here. Let's see. There we go. Let's take a look at that. It's same idea, but just a big, thick, heavy washer type thing. Again, more resistance to wear, and just a heavier duty kind of design. And this one has no weld repairs. Quite nice. One more item that makes this one better for our use. Let's try to find an ignition plug or an igniter hole. It's right there. You see how that's in fairly good condition? Right there? Fairly good. Really good. And the igniter hole, there's 2 of them. Here's one. Can you see how it's in the lower left-hand sort of quadrant? It's quite worn. It's very paper thin. It's made a sharp edge. So there you go. The design is a little bit heavier duty. I think more secure. And it's also in much better condition. So this combustor came out of one of the junkers on the pallet that looked horrible on the outside, and inside all the parts were in great shape. And I think our resurrected T58 race boat engine is going to be very happy with this combustor in it. From Maddox Turbines on a Sunday afternoon. Thanks for watching.
¿No vieron algún tipo de cámara de combustión? Vamos a ver esta que es de...
Okay, we've got a couple pieces in the shop that we don't see very often. So we're going to put them all together, and this is going to be a video about combustor liners. We're going to compare the way they're designed and the way they look. Okay, we've got the inner liner from an Arenda Type 14 turbojet. And there we've got the Rolls-Royce Spey. It's a more powerful engine by quite a bit than the Arenda. Then we have the standard or the old style can from a J79 right there. We have the new style can from a J79. This is the one that's used in all the LM1500 ground power units. Right next to it, we have our recently acquired J75 combustor. And shop
Yep.
kitty. Our J75 inner combustor liner with the 6 fuel nozzle holes. Very interesting piece. And Shop Kitty is showing us the LM2500 inner combustor liner. This is an annular design with 30 fuel nozzles. And, okay, Shop Kitty, she wants us to see the annular combustor liner out of a JFS 100 jet fuel starter. Very similar. It's an annular design, a lot smaller, a lot cheaper. You like that one, don't you? And right next to the new style can for the LM1500, we have a can from the Rolls-Royce Avon. It's a bit older, and it uses 8 combustors per engine rather than 10, so it's a bit larger. That's the overall view of the outside. Rolls-Royce Avon. Now, combustor liner design is a black art, and what I mean by that is, if you take all the equations and all the relationships of fluid dynamics, aerodynamics, thermodynamics, characteristics of fuel, fuel nozzle flow patterns, and what you want to do to burn your fuel and make your heat without burning up your engine, well, if you take all those equations and relationships and punch them into a computer, a supercomputer, you'll get a rough idea of what you want, but no specific design. It's very much trial and error. And so what happens is, with all those efforts and engineering teams working, all companies' combustor design starts to look kind of the same. We're going to take a look inside some combustor liners from different companies, different engines, and I'll show you what I mean. Okay, this is a J79 single fuel nozzle combustor. It's also using the LM1500. It's a bit black because it's been burning jet fuel, but it's got the mixing air holes, small ones up there. It's got a low velocity zone near the fuel nozzle, some large holes right there, small, and then the larger mixing holes here. These larger mixing holes are for mixing with the exhaust gases once the fuel is completely burnt. Up there's mixing air holes for helping to burn the fuel. Okay, J79. Now here's the liner from a Rolls-Royce Spey. It has the transition duct attached. This is what makes the gases take on the annular shape for the turbine. But we can look inside and you can see that it looks an awful lot like the 1500 or J79 design. It's got the fuel nozzle hole with the swirler vanes, the larger holes with little short ducts attached to them up top, and then progressive rings of mixing air holes to dilute the air, the hot air, to a temperature that the turbine can handle. Okay, that's the Rolls-Royce Spey. Okay, here's the Arenda Type 14 turbojet, and it also has the transition duct attached. We can look inside. Let's get the flashlight here. There's your fuel nozzle hole, your area of low velocity where the burning takes place, and then the progressive rings of larger and larger mixing air holes. This engine works at quite a low compression ratio, so it's a very large combustor liner. Looks familiar? That's the Arenda Type 14. And here's a look inside the combustor can from a Rolls-Royce Avon. It does not have the transition duct attached. And you can see there's the fuel nozzle hole with the swirler vanes, the cap with the low velocity area for burning of the fuel, and then the rings of progressive bleed air holes. Does that make it show up better? Bleed air holes for mixing of the hot combustion products with cooling air for introduction to the turbine. Okay, there's the Avon without the transition duct or the discharge nozzle, and it fits in the engine right like that. It doesn't actually stick together, the engine holds it together, and it produces the output area like that. Look familiar? Let's take a look inside the combustor liner from a J75 Pratt & Whitney. Look at that. Is that cool or what? There's the mixing air holes, the fuel nozzle holes with the swirler vanes around them. And I don't know what this is, but it's cool.
Es el turbinador.
Some kind of air swirler mixer. It's like a combustor liner inside a combustor liner. Look at that. Now this one doesn't have the discharge nozzle attached, but even though it's a little bit different in configuration, the overall design is quite similar, wouldn't you say? Okay, the Pratt & Whitney J75. There's a couple of interesting features of this Pratt & Whitney intercombustor liner. It uses 6 individual fuel nozzles, so it's a bit like a can type combustor liner and a bit like an annular type combustor liner. I don't usually see Pratt & Whitney parts here, so this is very interesting. Okay, here's the inner combustor liner of a JFS 100 jet fuel starter. It has 5 fuel nozzles, and you can see that the design is quite similar. Mixing air holes, with the larger ones near the end of the gas path. We're looking at the exhaust end of the combustor liner, and it has an integrated discharge nozzle. The combustor is in an annular shape, and the turbine is an annular shape, so you've got to have the gases come out as an annular shape. It's pretty easy when the combustor is annular. You don't have to have shaped ducts like the discharge nozzles for the can type combustors. Okay, and last but certainly not least, take a look at that. We've got the fuel nozzle holes with the little swirlers around them, and the progressive rings of mixing air holes. With the discharge in an annular shape, perfect for introducing the hot gases to the turbine. Can't really get this thing up on the table because it's heavy and it's expensive. The entire inner surface is covered with a ceramic thermal barrier, and that's a fuel nozzle hole. There are 30 fuel nozzles.
Los agujeros para atomizar.
Notice how many of them have an igniter hole. Let's see if we can find one. Oh, there's one. And there's one. This is a much more efficient design for more uniform burning of the fuel. This is an annular combustor, the type of combustor used in all modern large airliner engines. So there's a lot of advantages to an annular combustor. Better fuel economy, lower emissions, greater power, less stress on the turbine because it's a more even ring of heat going into it. But there's a couple disadvantages. The engine has to be removed and basically taken apart to replace or repair this liner, and it's expensive. Did I mention that this is worth $500,000? Yeah. Well, I hope you guys have enjoyed this, because I have. You don't get an opportunity very often to see that many kinds of combustors all in the same place at the same time. So it was a rare opportunity, and I thought I would take advantage of it for you. Once again, thanks for watching.
Ya vieron Bueno, ya ven casi todos los tipos de cámaras, más bien los 3 tipos de cámaras de combustión. Ok, nos regresamos. Ahora les quiero compartir la parte del... Déjenme ver. Que había puesto por acá. Pues que las figuras, todas las figuras que aparecieron antes están en los libros, son exactamente de los libros, no hay ningún secreto. ¿Alguna pregunta o comentario?
No, todo bien.
Bueno, vamos.
Por el momento todo bien, profesor.
No te escucho. ¿Qué dijiste, perdón?
No, que todo bien.
Ok. Ahora sí, déjenme ver. Vamos a poner el proyecto que les pasé de de turboprop, y ahí vamos a empezar a ver lo del cálculo, que van a ver que es una vacilada. Déjenme compartirles. Ahora no la veo. Ah, caray, ¿dónde lo dejé? Esta debe ser, ahí está. Sí se ve la tabla, ¿verdad? Lo tomé de los archivos de Teams.
Sí, sí, se ve.
Ok. Bueno, entonces, esta va a ser la última parte de cálculo. Y el dibujito. Vean ustedes, tenemos los datos de entrada. Ya sabemos cuál es el flujo básico que le toca. En el turbo prop es dato de entrada, eficiencia de la combustión, poder calorífico del combustible, temperatura máxima, que esto ya lo sabemos del ciclo termodinámico. También de nuestra gráfica, pues ya lo sabemos, ¿no? Datos que ya sabemos. Tenemos del ciclo, lógicamente, la salida de presión del compresor. Aquí está. La temperatura de salida del compresor. Sí, son datos de entrada. Los ductos del difusor que ya se seleccionaron apropiadamente. Ok. El diámetro de entrada que se proponía. Bueno, son parte de los ductos. Y los datos propuestos. Tenemos un factor, un concepto bien importante, que es el de intensidad térmica, ¿sí? O intensidad de la combustión, lo dicen otros autores. Entonces tenemos que es ¿cómo se llama? Que se tiene, cállate, se tienen se define con Quebec, subíndice Coca-Coca de cámara de combustión, y va de vean ustedes, estos millones, 40, sí, de los 30 a 40 millones de kilocalorías por metro cúbico. Esos son en unidades del sistema, vamos a llamarle internacional, aunque kilocalorías, bueno, del sistema internacional. Y tenemos otro rango. Ahora déjenme ver de qué. Es que en el libro no tenemos el libro de Stecking, que no lo tengo, no lo he conseguido digital. Es traducción de un libro, está en español, y es traducción al español de Mataix, que es un profesor de español, que traduce un chorro de libros también, precisamente de este libro sobre motores de combustión, motores de turbina de gas. Y como es traducción del ruso, tiene un montón de literales que no que de pronto nos confunden, pero son las mismas formas, pero tiene un montón de conceptos interesantes. Entonces, esto ya lo tenemos de nuestro ciclo ideal, ¿cierto? El número que ustedes van a seleccionar para la intensidad térmica es entre 30 millones y 40 millones. A mayor valor de la intensidad térmica, se tienen menores dimensiones, que es lo que queremos obtener, ¿cierto? Menor material y menor peso. Entonces, hay que jugar tanto con este valor, que lo usual y recomendable es ir directo a los 40 millones. Si fuera posible, después se le baja, normalmente no. Y la velocidad axial en la zona de la combustión. Este libro Stecking nos da un rango de 30 a 40 metros por segundo, está muy restringido. Y el Sarabanamuto nos dice que está de 30 a 60 metros por segundo, nos da más chance. Déjenme poner, bueno, ahorita ponemos el Sarabanamuto, para que vean que puede ser dado en otras unidades y en otro rango de valor esta intensidad térmica, pero vamos a manejar de 30 a 40 millones. Entonces, para todos los de turboprop, sugerencia, empiecen con 40 millones, y la velocidad, a menor velocidad también menores dimensiones, a mayor velocidad mayores dimensiones. Pues por eso directamente, por ejemplo, en este proyecto se fue a los valores extremos de 40 millones de kilocalorías por metro cúbico y de 30 metros por segundo para obtener las mínimas dimensiones posibles. Ahorita vamos a hablar de las dimensiones. La fórmula que aparece en los libros, si despejan ustedes de esta expresión el valor de intensidad térmica, simplemente pasan para acá y meten el volumen total de combustión acá. Esa es la fórmula que aparece en los libros, que dice que la intensidad térmica, si pasamos para acá, ¿verdad?, es igual al rendimiento de la combustión por el flujo másico del combustible, no del aire, abusados. El poder calorífico del combustible, si pasamos para acá, queda el volumen total por la presión de salida del compresor. Esa es la fórmula básica. Como ya estamos dando como dato de entrada la intensidad térmica, despejamos de ahí el volumen total, que es lo que queremos saber. Entonces, es el volumen total de combustión, todo el aire que entra y cuánto volumen necesita. Entonces, si lo despejamos, nomás que abusados con las dimensiones. Rendimiento de la combustión, pues sí, es 97%, es dato de entrada de cada uno. El flujo de combustible lo vamos a sacar de acá. Sabemos que la relación combustible-aire real, que ya la sabemos desde el ciclo termodinámico, es igual al flujo másico de combustible sobre el flujo másico de aire. Como también sabemos el flujo másico de aire, ¿verdad?, que para turboprop es dato de entrada, pues despejamos el flujo másico de combustible, ¿sí? Y aquí lo obtenemos, ¿no? Entonces, abusados con las dimensiones, no se vayan a hacer bolas. Aquí lo hice muy bien este proyecto, todas las dimensiones bien separaditas para que no, ya están aquí, masticadas y digeridas, ¿no?, para que las tomen ahí. El flujo másico de combustible está dado en kilogramos de combustible sobre hora, ¿sí? Porque, vean ustedes, está acá. Ahora, el poder calorífico del combustible en kilojoules sobre kilogramo de combustible. Pero como el dato ¿cómo se llama?, de la intensidad térmica está en kilocalorías sobre metro cúbico, aquí hace la conversión entre kilocalorías y kilojoules, abusados hace muchos años, hasta los años 80, al empezar los 80, existía la caloría grande y la caloría chica. Así se conocía. Y ya después se hizo una convención, pues, de unidades científicas, vamos a decirlo así, y se unificaron muchas unidades. De ahí tomó fuerza el sistema internacional. Ya no era sistema métrico nada más, no, sistema internacional. Y ahí se consideró que nada más considerar la caloría grande. Y la caloría grande o kilocaloría de pronto es de 4.184 kilojoules. Ok, entonces abusados con ese pedazo. Bueno, aquí ya está. También había que pasar la parte de la presión del compresor de salida a pascales. Y aquí está el factor de conversión. Sí, perdón, de pascales a kilogramos sobre centímetro cuadrado. ¿Ok? Porque aquí esta parte ya la vamos a tener en kilogramos. No, aquí está mal esta unidad. Es kilogramos sobre metro cúbico. Aquí me falta un factor ¿cómo se llama? De conversión. Porque esto debe haber sido kilocalorías sobre metro cúbico. Y aquí me falta un factor de conversión. No sé cuál le falta. Déjenme ver. Kilogramo de combustible se reduce. Kilojoule se reduce. La kilocaloría se reduce con la de acá que no aparece. Sí, y los kilogramos sobre centímetro cuadrado de aquí también desaparecen. Se reducen. Los pascales de aquí se reducen. Y esto debe quedar en metros cúbicos. De hecho, si ustedes ven, la intensidad térmica está en kilocalorías sobre metro cúbico. Aquí creo que aquí se equivocó. Esto es kilocalorías sobre metro cúbico. Para que estas kilocalorías se reduzcan a la unidad. Y las que sobreviven son los metros cúbicos, que es en lo que debe de quedar. Entonces, aquí está equivocado. Aquí debe ser kilocalorías sobre metro cúbico. Si no, esto no jala. Y al final, pues les queda el volumen total que se necesita para la combustión. Pero como tenemos un X número de cámaras de combustión, que corresponde a conectar cada una con un ducto de su difusor, entonces tiene que dividir y tenemos el volumen por cada cámara de combustión. Diseñando una, ya diseñan las otras, ¿verdad? Todas son igualitas, como ya vieron las imágenes en los videos, ¿no? Después viene el área máxima requerida. Aquí está la formulita. Como decía, este problema es de 4 fórmulas, o 5, si le queremos ver así. El área máxima se define como la constante del gas, aire en este caso, la temperatura del compresor, sí, que es dato del ciclo termodinámico, el flujo másico de aire, más el flujo másico de combustible, entre el número de ductos, por la velocidad, que ya se selecciona la mínima para las menores dimensiones, y la presión de salida del compresor. Ya tengo el área máxima. Con eso calculo el diámetro de la sección cilíndrica. Pues dame fórmula ¿cómo se llama? Del volumen del cilindro, calculo el área, el diámetro de la sección cilíndrica, ¿no? Ya tengo el área máxima y ya tengo el diámetro. Y vean ustedes de qué diámetro salen, de cerca de 10 centímetros de diámetro. Imagínense, ya son unos tubos quizá no muy gruesos, ¿no? O muy de mucho diámetro, más o menos delgadones. Ahora, el siguiente concepto importante es que La cámara de combustión, ahora sí déjenme ir al libro. Uy, ahora déjenme encontrarlo. Aquí vamos a abrir el Ahmed El Sayed. Vamos a cámara de combustión. Permítanme, ustedes no dejen de desesperarse. Aquí está Combustion Systems. Aquí está. Les comparto, permítanme. Ahí está. ¿Sí se ve, perdón?
Sí, profesor.
Ok.
Sí, profe.
Bueno, aquí. Ustedes ven los figuras que aparecieron en los videos. No hay más. Son todas las que aparecen en los libros. Entonces, repasando qué partes forman una cámara de combustión. La cubierta o caja externa, o que le llaman aquí el air casing, ¿sí? En las cámaras de combustión anulares, pues está la caja interna, ¿verdad? Aquí no, este es en tubular. El tubo de fuego, que es el que tiene los agujeritos. El torbellinador, para hacer precisamente turbulento el flujo aquí adentro, ¿sí? Que rodea o en medio lleva el atomizador, ¿sí? La bujía no es parte de la cámara de combustión, es parte de un sistema, ¿ok? Inclusive aquí está el agujero para la bujía, ¿ok? Son nomás esas partes para que vean que no son muchas. Ahora bien, la cámara de combustión tiene más o menos esta forma. Tiene una sección divergente, seguida por una sección cilíndrica y una sección convergente. Se considera que la sección divergente inicial ocupa bueno, sí, vamos a decir, ocupa el 10% del volumen total de la cámara. 10%, están las fórmulas. La sección cilíndrica es el 70%. Y la sección convergente es el remanente 20%. Ya todo suma el 100%, ¿verdad? Aquí viene la zona primaria, que es este pedazo, y la zona de dilución. Algunos le ponen, la separan también con zona de máxima combustión. Y vean ustedes que el aire secundario que entra por acá, vean, el aire primario que entra es el 20% que entra. El otro 80%, que es el flujo secundario para enfriamiento, entra por la periferia. Pero se va incorporando poco a poco. ¿Sí? Entonces, al final, pues vamos a tener quizás las proporciones invertidas, ¿no? El flujo secundario se tuvo que haber incorporado aquí todo, y quizá por acá salga un 20% y por aquí sale ya el 80% de todo el flujo que entra. Bueno, nos regresamos al cálculo. Entonces decíamos, el volumen de la sección divergente inicial es el 10.1 del volumen de la cámara de combustión que se calculó antes. Hay que calcularla. Después viene el volumen de la sección cilíndrica, que ya está aquí, ok, el 70%. Y de la sección convergente, el restante 20%. Aquí está. Entonces hay que calcular los tres volúmenes, ok, ya de una sola cámara. Después calculamos la sección cilíndrica, la longitud de la sección cilíndrica, pues que está muy fácil, ¿no? Del volumen es igual a área por longitud, pues despejamos la longitud, no tiene mucho chiste. Pero la sección divergente y la sección convergente es así, se consideran conos truncados. ¿Y cuál es la fórmula de cono truncado? Pues ya la ven ahí en su libro de cuarto, quinto de primaria. ¿Cuál es? Ya no me acuerdo. A lo mejor ya cambió, ¿verdad? Y no sé. Que nos dice que volumen de un cono truncado es igual a pi, ¿cómo va? Este es volumen. 1/3 de longitud sobre pi, no sé, 1/3 de longitud pi por radio mayor al cuadrado por radio menor al cuadrado por más el producto de los radios. ¿Sí? Entonces es un cono truncado. El radio mayor es la zona grande del cono y el radio menor es la zona de entrada, ¿no? La zona más pequeña. Pero aquí ya está masticadita la formulita para que vean. Ahora nada más hay que considerar lo siguiente. ¿Qué dimensión tiene el radio de entrada? El radio de entrada va a ser, recuerdan que en su dibujo, en su cálculo del difusor, determinan un área 3 de salida del ducto, de cada ducto, ¿no? Que es el que se conecta a cada cámara. Bueno, pues esa área, considerando la de sección circular, va a tener un radio y un diámetro, obviamente, ¿no? ¿Sí? Pues ese es el radio de entrada. ¿Ok? Y el radio de salida va a ser la altura del álave de la primera etapa de la turbina, que es donde se va a conectar la cámara de combustión. Salvo un adaptador, como algunos lo notaron por ahí, porque la cámara de combustión tiene una sección de salida circular. Y la turbina, la primera etapa, bueno, toda la turbina es de sección anular. Entonces, la sección inicial, el área inicial se llama, que tiene una forma de corona, ¿sí? Que son dos círculos concéntricos. O sea, hay que conectar esa sección circular al pedazo que le toca de sección de corona. Bueno, pues ese es un adaptador. Fue el que vieron ahí en el video, así medio raro, medio aplastadón, ¿no? Y muchos se preguntaron, ay, qué raro está. Pues sí, pues cómo conectas un área de sección circular de salida a la sección que le toca cubrir de la turbina, ¿verdad? Entonces, si son 12 12 cámaras de 12 ductos, como este proyecto, pues le toca cubrir la 12ª parte de la sección de corona. ¿Ok? Pero entonces el radio que voy a ponerle de mayor va a ser la altura del álave o la altura del plano 1 de la primera etapa de turbina. Y son estos datos que vemos acá. Diámetro de entrada es el diámetro que le corresponde, o radio, como le quieran calcular aquí, que le corresponde al área de salida del ducto del difusor, si fuera de sección circular. Y diámetro de salida va a ser igual a la altura del álave, pero en la altura del plano 1 de la primera etapa de su turbina gasógena, que es donde se va a conectar. Y aquí se la ponemos en el dibujo. Aquí va a estar.
Son las 8.
No le hagan 7:30. ¡Ay, qué exactos, oigan! Espérense ya nomás aquí. Entonces calculan la longitud de la sección convergente y la altura de la sección divergente, ¿sí? Y la longitud total de la cámara. Pero se debe cumplir que la suma de la longitud de la sección cilíndrica más la sección divergente no sea menor a un pie. ¿Por qué? Porque se considera, la recomendación es que un pie es la longitud de la flama o de la llama, para que no se salga de la cámara y le pegue al álave de la turbina, ¿no? Entonces, la suma que salga debe ser mayor a un pie, cuando menos un pie, ¿no? Pero si ya tenemos los datos o los conceptos de intensidad térmica como el valor más alto y la velocidad axial en el seno de la cámara de combustión como el valor más bajo, que son los que me dan las menores dimensiones, y aún así me sale de 50 centímetros, pues ya la cumplí. ¿Sí? Y después tengo que hacer el dibujito. Sí, donde tengo el tubo. Este es el dibujo más fácil, obviamente, ¿no? Vean ustedes. Ya más pongo las longitudes que calculé, el diámetro aquí de la sección cilíndrica, el diámetro de entrada, el diámetro de salida y la longitud total. Bueno, pues aquí le dejamos porque ya no están desesperados, ya dicen que son las 8 de la noche y no sé qué tanto están exagerando. Cualquier duda, comentario, le seguimos mañana. Ya pueden empezar a hacer su cámara de combustión los de turboprop.
Sí, profe,
Okay.
Gracias.
Bueno, nos vemos mañanita, cuídense.
Gracias, profe, hasta mañana.
No.
Profe.
Adiós. Bye.
Profe.